Good morning, dear children, and welcome to Vista's e-learning and online educational platform. My name is Denzil, your physics tutor for class 11. Let's get started with today's session. Today, we deal with a new concept, a new physical quantity called an acceleration. A quick recap from the previous session, we discussed a graphical representation for a distance-time graph. And from the distance-time graph, we learned how to acquire the information for a velocity. But this time, we shall see some of the other graphical representation such as a velocity time graph and also acceleration time graph. So let's dive into the session. This is actually a session 4 of the chapter motion, particularly motion in a straight line. So let's get started. So in the earlier concepts, we discussed one type of a graphical representation called a distance time graph. Now we learned how to acquire information of velocity by using what is called as a slope. So for that, you utilize two reference axes. Along the one axis, you have distance, and along the other axis, you have time. And by plotting a set of points, you can construct a straight line. Now, to identify the velocity, meaning finding the slope of this curve. So let me write that there, that identifying velocity is finding, not the red color ink. So let me pick a different color. I'll pick the color yellow. Slope in xt graph. Now when I use the word xt, x-t graph, it means distance time graph. Distance represented along the y-axis, whose SI unit is meter. Time represented along the x-axis, whose SI unit is seconds. But let's consider another case where we're trying to find the slope, but here I will use one of the mathematical tool called a limit. So here's what's going to happen. We have the same distance time graph. So let me put that as x in meters, t in seconds. After obtaining a set of points and plotting them on this graph, you can construct a straight line such as this. Now, when I take the slope in this given case, which is basically v, called velocity, the symbol for velocity, v. To be more specific, even more specific, we have to represent it by a vector quantity, therefore an arrow overhead. So this slope, which is a velocity, is obtained by delta x by delta t, where delta x is the difference along the y-axis considering the 2 points. When you take 2 points and you construct the projection along the y-axis, which is on the distance axis, you get x2 and x1 values. Similarly, if you take the projection along the time axis, you get two set of points, which is t2 and t1. Now, if I apply this particular tool called a limit, such that, now notice, for those of you who need more guidance on limit, I've conducted a bridge course where I introduce you a limit and slowly take you to a journey to a differential calculus. So go ahead, visit us at www.we-learning.in to look into more videos as such. I've conducted one of them, which is a bridge course where I give you an introduction to calculus. There I explained to you about the limits. So now we apply those limits. The limit, what I'm going to do in this particular case is set that limit for delta t almost tending to 0. I hope that is visible. All right, I hope that is visible to you. I'm going to apply a limit such that delta t is 0 for the given ratio delta x by delta t. In such cases, the velocity what you obtain is called an instantaneous velocity. So I'll erase the top part so that it is visible to you. So such a velocity where delta t, denominator, the time, almost tending to 0 is defined as an instantaneous velocity. This, on the other hand, can be written as, use a pen, this, on the other hand, can be written as dx by dt in a form of a differential equation. So this instantaneous velocity, how do we define it? Instantaneous velocity is defined as velocity of an object at that particular instant of time. To give you an example, it would be a speedometer. In case of a car or any automobile, they have a speedometer dial. And what you notice is that as you increase the accelerator or press on the accelerator pedal, the needle immediately increases. This is to show you that the velocity that it is showing is that particular instant of time only. So this is how an instantaneous velocity is defined by a limit where delta t is tending to 0, delta x by delta t, x by t. Simple? Now, what about its SI unit? Well, its SI unit would still be the same, which is meter per second. Or you can write it as an exponent form as a meter per second. What about it? What type of a quantity is it? Is it a scalar or a vector? It is certainly a vector quantity because it's velocity. So this is a vector quantity. So why is that for every physical quantity we are trying to determine a scalar and a vector? Why are we classifying them? That's because every single physical quantity are classified into scalars and vectors, even instantaneous velocity. So I hope I've made that easy. Moving forward, we carry on to the next, where we try to determine this velocity. Let's look at one example. Okay, I'll show you an example here. Let's consider this as a number line, and I hope you remember number lines from your lower classes. Okay, so 0 at the center, set of all positive integers towards your right hand side, and set of all negative integers towards your left hand side. So let's mention 1, 2, 3, 4, 5, 6, and then you have -1, -2, -3, -4, -5. All right. Now, a car, so let me draw a car. I'll do my best, though I'm not an artist. I'll do my best to represent a car. And not too bad, isn't it? Okay. Maybe a nano car or things like that. A car which starts at 0 moves in a positive direction. Now, it moves in such a way from 0 to 1, it takes 1 second. 1 to 2, it takes 1 second. 2 to 3, it takes 1 second. So what type of a motion is it executing, this car? You guessed it right. It is trying to execute what is called as a uniform motion, where it is covering equal distances in equal intervals of time. Therefore, uniform motion. And when it comes to determining how fast this car is moving, what we need to do is identify its speed. So, speed in a given direction is nothing but a velocity. So, let us try to determine the speed. We already know the direction, which is along the positive x-axis. So, the speed in this following case, or let me just write velocity because we know the direction. So, velocity, which is equals to plus, can you guess how much? Go ahead, try to calculate from 0 to 1, 1 to 2, 2 to 3, what would be its velocity? You can find what is its average velocity, but I don't want the average velocity. Velocity at this particular distance, velocity at this distance, and so on and so forth for every 1 second. When you calculate, you will obtain that the velocity will be equals to 1 meter per second. Velocity is plus 1 meter per second. So what type of a motion again? A uniform motion. Now let us do one thing. We will take this set of information and plot it. Okay. Now, how is velocity changing over time? Velocity in the first moment is 1 meter per second. Oh, I'll change the ink. Okay. Velocity at the first moment is 1 meter per second as the time is 0. Then velocity is still 1 meter per second as time progresses to 1 second. Velocity is still 1 meter per second as the time progresses to 2 seconds. Velocity is still 1 meter per second, time is 3, velocity is 1 meter per second when time is 4. You observe that the velocity here does not change. It's a constant velocity that the object is trying to accomplish. So now that we have this set of data, let's plot them in a graph. So, graph sheet, what must it consist of? Your y-axis and the x-axis, your ordinate and abscissa. Now, what do we represent? What physical quantity can we represent along the y-axis? Since the type of graph we are trying to achieve here is a velocity time, we represent the y-axis by velocity. Velocity whose unit is meter per second. Similarly, along the x-axis, what physical quantity can you represent it with? Time. And what is the SI unit of time? Seconds. Now, let's fill in the other digits. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, and 6. Right? Now, let's have a look at the data. When time is 0, velocity is 1 meter per second. Time is 0, velocity 1 meter per second. Time is 1, you can have a look at it. Time is 1, velocity is still 1 meter per second. Time is 2, velocity is still 1 meter per second. Time is 3, 4. So you get this horizontal line which is parallel to the time axis. We also observed a horizontal line parallel to time axis in case of a distance time graph. So in a distance time graph, if it is parallel to the time axis, what does it tell about the state of an object? It means that the object is at rest. But in this case, it is not distance time, rather it is velocity time graph. So when a line is parallel to the time axis for a velocity time graph, what can we say about the object state? That it is moving in a uniform motion. So remember that it is moving in a uniform motion, or simply constant velocity, that it is moving with a constant velocity. I hope I've made this clear. In this particular case, for a velocity time graph, an object moving the constant velocity executes a uniform. Now, what if the case was different? What if it's no longer executing a uniform motion? Let's take a look at that by an example. Here again I have my one dimension, a number line on which I represent a set of positive integers towards your right hand, a set of negative integers towards your left hand. 1, 2, 3, 4, 5, 6, 7, 10. -1, -2, -3, -4, -5. Now these numbers here no longer represent the distance. Keep that in mind. In the previous case, we assumed it was distance. But these numbers, what I've written here, they no longer represent distance. They represent the velocity. So let me write that here, velocity, which is in meter per second. Okay. So they no longer represent the distance, they represent the velocity. So what is happening here is that this car, which is at zero velocity starting from rest, changes its velocity to 1, to 2, to 3, to 4, to 5, to 6. That means its velocity is increasing as it is moving away. All right. So since the velocity is increasing, how fast is it increasing with respect to time? From 0 to 1 meter per second, it takes 1 second. 1 to 2 meter per second, it takes 1 second. 2 to 3 meter per second, it takes 1 second, and so on and so forth. So these data, let's put them in our table. Velocity, since it is starting from 0, so I'll write 0. Oh, change the color, change the color, change the color. Starting from 0, time is also 0. Then it moves to 1, which is 1 meter per second. Okay, it changes to 1 meter per second in what duration? 1 second. Then it changes to 2 meter per second in what duration? 1 plus 1, 2. Then it changes to 3 meter per second in 3 seconds. Similarly, 4 meter per second in 4 seconds. Voila. So here we have a case where the velocity is increasing. So it is no longer in a uniform motion state, isn't it? This is no longer in a uniform. So since it is changing its velocity, let's try to plot them on a graph. So a graph will consist of two axes, one which is called y-axis and the x-axis, and along the y-axis we represent with the velocity. Now you may complain and say, sir, it is difficult for us to write the whole word velocity. It consumes too much of space and time. Well, not to worry. We have a short to denote this velocity and time. Velocity time is given by Vt. So in instead of writing velocity time graph, short and sweet, you write VT graph. So VT graph. Easy. For a distance time graph, you call it XT graph. For a velocity time graph, you call it a VT graph. All right. So now it comes to plotting. Along the y-axis, we have velocity v in meter per second. And along the x-axis, you have time t in seconds. Okay. Now, the numbers, insert the digits 0, 1, 2, 3, 4, 5, and 6. And then you have 1, 2, 3, 4, 5, and 6. All right. Now we plot the points. The first point is 0, 0. Yes, at the origin. Then 1, 1, 2, 2, 3, 3, and 4, 4. All right. Join the points and you get this beautiful straight line. See how nice it looks, the straight line. Okay. Now, here's the best part. By taking the slope on this, curve, so I hope you remember slope, yes? By taking the slope on this curve, the physical quantity that you obtain is what is called as an acceleration. So how do we define an acceleration? Acceleration is defined as the rate of change of velocity. As the velocity changes, then it gives rise, as the velocity changes with respect to time, let me correct that. With respect to time, it gives rise to a new physical quantity called acceleration. So let's have a look at it by a standard definition. Acceleration A, I'll choose a lighter color ink. Okay, eraser ink, lighter. The acceleration is given by the symbol A. Okay, first I'll write acceleration. That's a C, all right? It's given, denoted by the letter A. Acceleration is a vector quantity. Therefore, you put an arrow overhead. Since it's a rate of change of velocity, velocity itself is a vector quantity. Therefore, acceleration is a vector quantity. Again, it is defined as what? Rate of change of velocity or change in velocity, either way. So you get delta V by delta T. This is how you define the rate of change of a given physical quantity, in this case velocity. The rate of change, remember, always occurs with respect to time. So delta V by delta T. Delta V, you're quite familiar, no problem, which is nothing but V2 minus V1. And delta T, vector quantity. Delta T is T2 minus T1. Now this is how you define an acceleration. Now what about its SI unit? The SI unit of a velocity is meter per second. Since time is in the denominator, which is again into second, meter per second times second is meter per second square. SI unit is meter per second square. You can also put this as an exponent form where you get meter per second. All right. So this is a general definition of an acceleration with its respective SI unit. How do we find acceleration in a velocity time graph? By finding slope. So if you select any 2 points on the curve, you select any 2 random points on the curve. So let's say I take this point and this point here, and then you construct a slope, identify the respective v2, v1, t2, v1, and then what you obtain by dividing one another is acceleration, or is acceleration A. Simple method. So this is why we require a graphical representation where we can identify the other physical quantities which are not known. So yes, and one more thing about representing a graphical method is you can identify a quantity which is also a displacement. How do you determine displacement in case of a velocity time graph? Let's take the two reference axes, namely your y-axis, x-axis. Since this is a velocity time graph, your y-axis will be represented by velocity v. Time axis will be along the x-axis in seconds, in meter per second. Then what you do is obtain a set of points by using the table, remember. So you obtain a set of points, and those points you try to plot it on the graph, and you construct a straight line like this. So everything up to this point is okay. Can you find acceleration? Certainly, why not? You can find acceleration only up to this point. As you notice, the velocity is increasing. Since the velocity is increasing, there's a change in velocity in a given amount of time. Since there's a change in velocity, there is acceleration. But from here to here, the object is trying to move at a constant velocity. So there is no change in velocity. If there's no change in velocity, then there is no acceleration. So no acceleration at this point, there's acceleration only up to this point. Now, our purpose here is to find displacement. How will you determine displacement from this given graph? Displacement can be found by determining the area under the curve. This is the curve. The area under the curve. Well, first of all, when you try to construct, you get a trapezium, but the trapezium can be split into parts which is more recognizable, such as a triangle and a rectangle. So all you have to do is find the area of this triangle and then find the area of this rectangle. By determining these two area of these two objects, these two plane figures, you obtain what is the area, what is the displacement. Okay, so displacement in this particular case will be equals to area of triangle plus area of rectangle. Easy. So this is how you find the displacement in given velocity time graph. Now, similarly, to find acceleration, try to recollect, you determine it by slope. Okay. 1 second. Velocity again. Wait a second, what's happening? All right. So displacement is determined area under the curve for a velocity time graph. Now moving on to acceleration. How can we determine acceleration? Very simple, is by taking the slope. Arey yaar, why is it vanishing? Seems to vanish. Come on. One moment, just give me one moment. All right. How do we identify acceleration in a velocity time graph? Recollect, velocity in meter per second along the y-axis, time in seconds. You obtain a straight line by plotting a set of points, and then you find what is the, guessed it right, slope. Okay, find slope. So you draw a projection along your y-axis and projection along the x-axis, meaning the time axis. So you get two set of points along the y-axis or in the in the direction of the velocity as v2, v1, similarly e2, e1. Where slope, in this case acceleration, a vector, which is equals to v2 vector minus v1 vector divided by t2 minus t1. Okay, so these are vector quantities. So this is how you can identify acceleration. Now, is it possible for us to plot an acceleration time graph? Certainly, there is a possible way where we can find acceleration time graph. For that, let us look into one example, one simple example, how an object exhibits an acceleration. Now, where can you feel this acceleration? Can this acceleration be felt? Yes. In fact, when an object tries to accelerate, there's a force that acts backward. Though this chapter is nowhere related to force. We're not going to discuss about force, but I'm only talking about the experience that you feel. So when you accelerate forward, you feel a force acting backwards. It's an experience. So in case of a roller coaster, when a roller coaster goes down, it accelerates, what happens to you is that your body gets pushed backward. So it is possible for you to experience this acceleration. Yes, okay, it's because of a force that acts backward. Now, how does an acceleration vary? Can it be a constant acceleration? Can it be a variable acceleration? Yes. Let us look into one following example. Change the color to yellow. Okay. Okay, so I have a car. Okay. A car initially accelerates to 1 meter per second. Let me write the number there rather. A car accelerates at a constant unit. So initially it accelerates to 1 meter per second square, to 2 meter per second square, to 3 meter per second square, 4 meter per second square. But this doesn't seem like a constant acceleration. Apologize for that. This is not a constant. Wait. One moment, everyone. This is not a constant acceleration. So sorry. 1 meter per second square, 1 meter per second square, and 1 meter per second square. This is a constant acceleration. Now the object is constantly trying to accelerate. So in the first second, accelerates to 1 meter, next second 1 meter per second square, in the next second 1 meter per second square, and so on and so forth. Now plotting this in a set of tables, I've already put the graph there. By plotting this in a set of table, you will have 1 acceleration 1 1 1 on one side, and on the time you have 0 1 2 3 4 because the time is progressing, so you get 0 1 2 3. And by plotting those set of points on a graph sheet, you get a straight line which is horizontal and also parallel to the time axis. But which one is the time axis? Remember, it's the x direction, the time axis. And along the y direction, you have acceleration. So this is a graph of an acceleration time graph. This is an example of an acceleration time graph, or simply we call it AT graph. See? So you have three different types of graph, one called XT, VT, and now AT graph. Now what if the acceleration changes at every given moment? 2 to 3 to 4. Or it could also decrease. Well, these are variable acceleration. So in this case, you do not get a constant acceleration, whereas an acceleration can vary. An example of this variable acceleration is noticed on a roller coaster. Initially, when you go down, and then when you slowly start going upwards, well, there's a different acceleration. Once you have an acceleration that is increasing, acceleration which is in a downward direction, and then you have an upward direction. So in that way, you have a variable acceleration. Or it could also be a driving a car. When you drive a car, you accelerate, and when there's traffic, you apply brakes. So you have this variable acceleration. So if an object is speeding up, we call it accelerating. Okay, so it is accelerating. But if an object is slowing down, then it is called decelerating. Nothing to worry about these two terminologies. We will soon see that later in the next session. Now, how do we determine velocity using acceleration time graph? For an acceleration time graph, velocity can be determined by area under the curve of an acceleration time graph. Area under the curve. Do you remember area under the curve for a displacement in a VT graph? Similarly, in an AT graph, find the area under the curve, get velocity. Okay, so cut them into parts. So now you can determine the area of this triangle as well as the area of this rectangle. So by identifying these two area of plane figures, you can find what is the velocity of an object. Good? Easy? Well, let's do OA. Supposed to have. So we will do a quick recap. We were supposed to do the recap, yes, see. So let us do a quick recap from the beginning of XT graph, VT graph, and an AT graph. In case of an XT graph, change the ink. So a quick recap, XT graph, we discussed three different types of graph. One, where the line was parallel to the time axis. This is for an object at rest. Second, we noticed for an XT graph, a linear curve, an increasing linear curve like this, is for an object which is moving at a certain, which is in motion. So let me write that as in motion along the positive direction. So velocity can be determined in this case by using slope. So I'll write here that slope in this case gives velocity. Okay. And also one last for an XT graph. XT graph, line that is pointed downwards. This is also for an object in motion. But how different is it from the previous? Is that they're moving in different direction. This is moving along a positive axis. This is moving along a negative axis. Therefore, by identifying slope still gives you velocity, but in negative direction. This would be a positive direction. Yes, so I have made it easy. 3 different states for an xt: at rest, in motion, increase in a positive direction, in a negative direction. Finding the slope gives you velocity. Now let's have a look at VT graphs. So in case of a VT graph, let me start from here. In case of a VT graph, we observed that if the line is parallel to the time axis, this represents constant velocity. Okay, and then in the other case, VT graph, you get changing velocity. For a changing velocity, this is changing velocity. In case of a changing velocity, finding the slope gives you acceleration. Finding the slope gives you acceleration. Area under the curve. Area under the curve gives you displacement. Collect slope, area under the curve, giving rise to 2 different physical quantities. Similarly, you can also construct a velocity time graph. So I'll draw it here, a velocity time graph, but in this case, a curve that is pointing downwards. Okay, this curve that points downwards tells you that the object is slowing down. Here it is speeding up. So let me write here, speeding up. Here it is slowing down. Finding the slope and also area under the curve gives the same 2 physical quantity called acceleration and displacement. But since the object is slowing down, we no longer call it an acceleration. Rather, we use 2 words. I mean, you can use one of them. It is retardation or deceleration. So the 2 words you can use called retardation or deceleration. Okay, so these are the 2 words that can be used, retardation or deceleration, to show that the object is slowing down, meaning its velocity is slowly decreasing. Area under the curve, even for this, still gives you displacement. Okay, so this is for a velocity time graph. Now let's look at acceleration time graph. What are the different acceleration time graph that we discussed? One moment before I end the session. Acceleration time graph. A T. One where you have this shows you a constant acceleration. Area under the curve gives you, for an acceleration time graph, area under curve gives velocity. So how do you find area under the curve? See, you have a recognizable plane which is a rectangle. Find the area of rectangle, you find what is the velocity in this particular AT graph. So area under the curve gives velocity. Can you find the slope in an AT graph? Even if you do find the slope in an AT graph, it has no meaning to it because there is no physical quantity for an AT graph. All right? Oh wait, why is it in a hurry? All right. So this is about one of the AT graphs. Now I will show you one last type, how AT graph, how acceleration is represented in an XT graph. We learned, if you look back, I'll show you, if you look back, we learned how to represent velocity. Here we have, we learned how to represent velocity on an XT graph, and we represent acceleration on this XT graph. Yes, we can represent acceleration on an XT graph. For that, a small concept that I'm going to discuss related to our differential calculus. First, we notice that V can be defined by dx by dt, called the instantaneous velocity. Correct? Similarly, acceleration A at particular given instant of time can be identified by dv by dt. And since we know already what is v, so if you substitute in that place, you get times dx by dt. This is x, which is displacement, also vector quantity. You get d square x by dt square. So this is how acceleration is related to displacement. So first I wanted to show you this relation before we could plot. I wanted to show you this relation and then we can proceed with plotting. Okay. So this is how acceleration is related to displacement. So now let us plot. Okay. In an XT graph. Positive acceleration, increasing acceleration are usually in a form of a parabolic curve. A parabolic path, you see, yes, this is increasing acceleration. Though it is moving an exponentially, it doesn't necessarily have to move exponentially, but rather a simple parabolic path. So let me try to draw that again. Now, if it is slowing down, meaning that there's a retardation, in that case, so let me write this, positive acceleration. If it is slowing down, I'll represent it here. If it is slowing down, there's a retardation. Therefore, you get the path which is close to this is a negative acceleration. So now I've taught you how to identify three different types of graphs, and from those three different types of graphs, how to determine the new physical quantities, and also using those graphs how to relate one another, such as in this case as an acceleration and a xt graph. So that is all I have for today. I hope I've made it clear. So do visit us at www.v-learning.in to get more details about the classes. You can go back and have a review at the bridge course where I've explained to you about some of the concept related to differential calculus and also introduction to limits. So I'll see you all in the next session. Until then, take care and bye-bye.